Hello everyone and welcome to my channel. As you can see right here, I have my spectrum analyzer, an HP 8560A, which allows me to measure signals from 50 Hz up to 2.9 GHz. I bought it on eBay back in 2022. It was faulty, but it will still power on and display several error messages. It was also missing its feet and handle, but apart from that, it was complete. Once I had it in my hands, I had no choice but to order a Yig oscillator from eBay because the original one was completely dead. Someone had apparently tried to repair it before without success, since the Yig sphere itself was missing. These oscillators are often very expensive on eBay, but luckily at that time I managed to find one at a reasonable price, which helped keep the overall repair cost under control. In the end, it was a break-even operation financially, but I got a lot of satisfaction from repairing and recalibrating the instrument. And honestly, that break-even lesson didn't really stick with me, because today, as you've probably seen in the title, I'm diving back into rebuild another analyzer, this time an 8563A. This one will let me measure signals up to 22 GHz, although I will lose the ability to measure very low frequencies since it starts at 9 kHz instead of 50 Hz. But that's not a real big issue. So my idea was to find a cheap 8563A and use my 8560A as much as possible to cover for any missing parts. I eventually found one on eBay from a seller in the US. The unit was in pretty rough shape. From the photos, several parts were missing, but all of the electronic boards were still there. On the other hand, a large part of the RF section was gone, including the Yig oscillator, which, as you can guess, was no surprise. So yes, I gave in and broke the piggy bank. I imported what was left of this instrument, and today I'm bringing you a sort of fake unboxing, because I've already opened the box and ordered some missing parts, but still an unboxing of sorts. This box will be sticking around with me for a while during this project, and it will also serve as a storage for the analyzer's carcass between repair sessions. Space is tight at home, so I have to pack everything away each time. So, is this swap a good idea? Probably not. Will it be profitable? Definitely not, but I hope it will be interesting for both you and me. So without further ado, let's get to the unboxing. Let's take a look inside the box together. We can already see that the top cover is missing. I pull the unit out a bit so we can see it better. Well, it matches the seller's photo pretty closely. As expected, the RF connector is missing, probably taken along with the attenuator. The screen is oddly dirty. The seller, in his great generosity, provided the high voltage power supply for the CRT display, so thanks I guess. Let's pull it out and take a closer look. I'll start by inspecting the A2 controller board, and right away I see something I don't like. A component is missing here. It looks like it was removed cleanly, but I don't know why it was taken out or how much of a problem it might cause for this project. Looking inside, I can see what's missing is a DIP 14. Apart from that, it seems that no other components are missing from the A2 and A3 boards, which are the controller and interface boards. I'm glad that all the firmware EEPROMs are still there. That makes me confident on the analyzer's ability to boot, unless of course the missing component prevents it. I'm being very careful when opening the boards. On this instrument, the boards open 2 by 2 since they are connected together with hinges that require handling them this way. Continuing the exploration, it's clear that the power supply board is missing. That doesn't surprise me at all because not only it is hard to find, it is also very expensive and therefore highly sought after. I haven't been able to find a single affordable one on eBay. This is just reinforcing my plan to use the 8560A as a donor for this project. I've put back together the controller board and the top section for now, so I can focus on the RF section underneath. As expected, quite a few elements are missing here as seen in this picture. Notably this one, the dual mixer, A8 on the schematic, which I've already ordered. When shown in the correct orientation, you can see a series of voltages written on the front. These are calibration or biasing voltages specific to this dual mixer, and the analyzer will need to be adjusted to those values later on. So I'll go ahead and install it now, which kind of marks the start of this analyzer rebuild. I also ordered from RS a set of screws identical to the originals, which were missing from this unit. At this point, I realize I won't have all the rigid SMA cables needed for this rebuild. I need to find a solution. Let me open a parenthesis here to guide you through the RF block diagram. Normally, the signal enters through the RF connector, which is missing on my unit, then passes through the attenuator, also missing, which is made of different resistor combinations, allowing attenuation from 0 to 70 dB in 10 dB steps. Next, it goes into a band selector, a mechanical switch, which is still present. This switch selects between two frequency ranges, 2.7 to 22 GHz for the high frequency path, or 1 kHz to 2.9 GHz for the low frequency path. The low frequency path is identical to the one of the 8560A. For the high frequency path, the signal then goes through a tunable bandpass filter based on the Higgs sphere called the YTF or Higgs tuned filter. This filter narrows down exactly around the frequency being observed. For example, if my input signal has a component at 9 GHz, when the analyzer sweeps across that frequency, the YTF will be centered on 9 GHz with a bandwidth of 20 to 40 MHz. Since the analyzer uses harmonic mixing, it's crucial to eliminate nearby signals, otherwise other frequencies could fall into the same IF band and distort the measured amplitude. The signal then reaches the high frequency mixer, the A8 dual mixer module, which I just reinstalled. Each mixer has its own local oscillator or LO input, coming from the A11 Higgs oscillator or YTO I mentioned earlier, whose output is amplified and distributed by the A7 LO distributor module. The dual mixer, therefore, contains two mixers, one for each band, and it uses pin diode RF circuitry to switch between the high and low frequency mixers. The output signal is called the IF or intermediate frequency. The point is to bring a very high frequency like 9 GHz down into a range the electronics can handle, in this case 300.7 MHz. To achieve this, as in my earlier example, you subtract 9 GHz from 8.6893 GHz. Since the LO local oscillator fundamental varies from 3 to 6.81 GHz, it must be set precisely to 4.34465 GHz, which, thanks to its second harmonic, helps us to obtain 310.7 MHz. That's why the YTF is so important. Without it, if my signal happened to have a component, for instance, at 4.65535 GHz, it will also be converted to 310.7 MHz via the halo's first harmonic, creating a false amplitude at the mixer output. That wraps up this first look at the RF block. The second part will come later, once I finish reassembling this section. Back to the assembly. I've ordered the attenuator with the correct reference number according to the service manual. These attenuators are easy to find on eBay, but they are also very expensive. So I ordered a faulty one, hoping I can repair it using the one from the 8560A. Hopefully that works and helps keep costs under control, because I really don't want to overspend on this project. Bad news. As you can see, the power switch is broken in two. That's yet another part I will have to salvage from the other analyzer. Anyway, that's it for now for this section, and I will put it back together before moving on to another part of the instrument. Now I'm tackling the front panel. It's really dirty. I also want to reinstall the RF connector by taking it directly from the 8560A. By comparing the service manuals of both analyzers, I was able to confirm that it's indeed the same part. I already removed the screws on the other side, so now I just need to take out these three here. As you will see, I really shouldn't have done that. While pulling the front panel, I unfortunately bent this semi-rigid cable. It still looks okay, but I will need to be more careful. And yes, I'm using an adjustable wrench here, but it's only temporary and it's just to loosen the connectors, so it should be fine. Here's the front panel finally removed. You can see the different elements that make it up, including the semi-rigid cable I bent earlier. I need to screw the volume control back in place and reinstall the RF connector. I'll also take care of cleaning the CRT screen window, which really needs it. Since the front panel is removed, I'll also take the opportunity to position the attenuator. And honestly, I really enjoy seeing the instrument like this. It lets me appreciate the remarkable work of HP's engineers who managed back then to make this analyzer so compact by maximizing the use of space. You can see that every board, every module has its precise place, leaving almost no empty space. And above all, these elements don't interfere with each other. That's also why there is so much shading inside, especially around the CRT display. While I'm at it, I'll also clean the attenuator. Now the two analyzers are side by side. This is the last time I'll see the 8560A complete, since I'm about to dismantle it. I now have access to the RF section of the 8560A. Having learned from my mistakes, I'll start by disconnecting all connectors linked to the front panel. Looking more closely, you can spot the YIG oscillator on the left. The large grey bar is the second converter with the FL2 low-pass filter at 4.4 GHz, which connects directly to the mixer on the right, itself connected to the local oscillator output further to the right. You can also see the attenuator at the bottom along with the cable linking it to the RF input, which you can just make out. I'll also salvage the power switch, which is still in good condition. Next, I need to disconnect the keyboard cable from the controller section, and I'll take the opportunity to recover the screws as well. Now I have full access to the display and the power supply section underneath this cover. The label on the CRT shows more adjustment potentiometers than the other one, but I don't think that will be an issue. After removing the power supply cover, you can clearly see the supply itself, along with the high voltage supply we saw earlier in the box during the unboxing. I was wondering which CRT to keep, but since the one from the 8563A is quite burning, as you can see here, I go with the one from the 8560A instead. At this point, it's the 8560A that ends up in the box. So I installed in the 8563A the CRT board A17 along with the CRT display from the 8560A, replacing the one that originally came with it. This conveniently resolves the potential compatibility issues I mentioned earlier. I also reinstalled the power supply board, but I haven't fitted the Cal oscillator board A16 yet, as I still have doubts about it. I've put the instrument back together, and in the meantime, I received this eBay order, a bundle of cables from another 8563A. That's particularly convenient since it includes the rigid SMA cables I was missing, along with other wires and ribbon cables that will no doubt come in handy over the course of this project. I find it rather amusing that while some people dismantle these analyzers to sell the parts, others like me buy those very parts in an attempt to rebuild the original instruments. I also need to properly secure these hinges, since everything was previously taken apart and reassembled rather carelessly. A few screws are missing, so I replace the remaining ones with the new screws I bought, starting fresh with a solid base. Looking closely, you can see that the screws need to be placed inside when the boards are open. On the right side the screw is there, but not on the left. Quick aside about this connector, it normally links the CRT board A17 and the Cal oscillator board A16, but the latter is missing here. Another interesting detail is that on the 8560A the speaker is connected to the Cal oscillator A16, which also houses the AM/FM modulator, whereas here it's connected, let me move the camera, there, to board A3. This is most likely a design evolution, suggesting that the Cal oscillator is now integrated into board A3. Back on the RF side, I'll now start connecting the modules together using the cable I received. It's a bit of a puzzle to figure out which cable goes where. Even though the service manual shows the layout with model numbers for each cable, the cables themselves have no markings, so it's going to take some trial and error. For example, I try this one between the attenuator and the RF switch, but it's not the right one. But this other one looks right, and the lengths of each side match perfectly, so I go ahead and install it. Here's what it looks like now, thanks to my new stock of cable for this analyzer. Definitely no regrets about that purchase. I'll keep going. This one seems to go on the other side of the switch, judging by the picture. With that, the input of the filter FL1 is once again connected to the RF switch. I'll finish wiring the switch by connecting the other side, which should go to the YTF bandpass filter. And since it directly handles frequencies up to 22 GHz, it requires a thick rigid SMA cable. Thick because I've noticed that the cables handling the higher frequencies are indeed thicker than the others. This one looks like to fit perfectly. Great, another step completed. The RF switch section is now wired. The input of the second converter, here, needs to be connected to a low-pass filter FL2, which in turn connects to the output of the dual mixer. According to the service manual, this should be a single piece cable, which I don't have in my stock, so I leave that for later. Back to the first filter, FL1, I found the right cable to connect its output to the input of the dual mixer. Now I just need to connect the output of the local oscillator A7 to the input of the dual mixer A8, located underneath, and I found the right cable for that. After nearly completing the RF wiring, it's time to tackle the controller section and reconnect all the elements. I've placed the 8560A back next to me to help to trace the cabling and wire routing more accurately. I'll open up both units and compare them side by side. I haven't mentioned it earlier, but this CRT cable is also part of the batch I purchased. However, the connector includes the keying features that doesn't fit into the CRT board from the 8560A. You can clearly see it here when comparing the two. Does this difference imply an incompatibility between the A2 board of the 8560A and that of the 8563A, or is it simply a design evolution? Finger crossed, it's the latter. Meanwhile, I reconnect the other cables like this one, which I think goes here. Perfect. Now reconnecting the brown one. Done. This one is stuck underneath in the RF section, so I'll need to go around to the other side to retrieve it. For now, I can see the end of the cable, so I'm trying to feel for it, but no luck. Ah, there it is. I loosened the front panel again to pull it back up. Got it! Yes! Time to reattach the front panel. Let's go! Now I need to figure out where this one goes. According to the service manual, it should go up here. I'll double check with the other analyzer to be sure. Ah, right, it has to pass through here. Okay, let's do it again. There we go, another step down. This whole section looks properly wired. I'll check the connection now. Alright, I've checked everything and it all seems well connected. Since I'm here, I'll also swap out the GPIB connector. I'm not sure if you can see it clearly on camera, but the ribbon cable is damaged in one spot. It's not a big deal, but since I'm at it, I'll replace it. And here's the other one in much better condition. There are also clips to hold the cables in place and a sleeve to route the CRT and CAD oscillator ribbon cables. That's another good step done. I'll reuse the sleeve, even though I think only the CRT ribbon should go through it, since apparently there's no A16 CAD oscillator board in this model. Still, it will protect the ribbon and honestly, it gives the instrument a nice look. I'm happy. It's really starting to look like a complete instrument now. By the way, I noticed that on the other analyzer, there was a clip holding boards A4 and A5 together, so I'll salvage that one as well. That's it for this section for now, so I'll close it up. The module extension cable is still bothering me, so I won't reconnect it just yet. I also only put one screw in to hold the boards for now, since I still need to wire the display. Alright, let's switch back to the RF side, this time on the 8560A. I still need to install the FL2 low-pass filter, but I had some doubts about it. As we saw earlier in the 8563A service manual, FL2 will be a fully integrated filter, whereas in the 8560A it's a separate filter connected with two rigid SMA cables. I think this is a design evolution and I'll reuse this one, since both filters have the same cutoff frequency, 4.4 GHz. While installing the filter, I remembered that in the bag they received, there were some small rigid SMA cables I hadn't identified. Since they fit perfectly here, I'm not certain this is the right filter and that the service manual I have corresponds to an older version. Now comes the transplant. I'm exaggerating a bit, but this YIG oscillator is really the heart of the system. It oscillates between 3 GHz and 6.81 GHz, and thanks to the harmonics, it can reach up 27 GHz. This one is a 50867781, specific to this family of analyzers. I'm not sure how compatible it is with the 8560E series, but they look very similar. I could reuse the cable from the other unit, but since I have some in the bags I received, I'll look for the right one. This one fits, the keying tab is in the right place. Now I just need to install everything. The oscillator is now in place, but I couldn't secure it since it mounts from the other side. I now realize I forgot to connect the ribbon cable to the attenuator. Let's see if I have one in stock. I had to remove it again. Looking at it, I'm not sure how to wire it, since there's no input or output marked on it. It has to be mounted the opposite way compared to the 8560A, judging by the ribbon connector here. I have to salvage this ribbon from the other analyzer, since it's missing from my stock. Alright, it's connected now. I just need to figure out the routing for the ribbon. Next step is to connect it to the frequency control board, and the analyzer is now complete again. I'll also tidy up the cables and tighten the SMA connectors, not to torque spec, since I don't have the proper wrench, but with the size 7 wrench I had in my stock, which works fine. Now that the RF section is complete and wired, let's take a second aside to look at the rest of the block diagram. We left off at the outputs of the dual mixer A8. To recap, after mixing, we get an intermediate frequency IF of 310.7 MHz for the high band and 3.9107 GHz for the low band. The latter passes through the 4.4 GHz FL2 low-pass filter I've just finished wiring. Its role is to attenuate unwanted high-frequency components, especially harmonics, before entering the second converter A13. In this converter, if the IF is already at 310.7 MHz, it just goes through a low-pass filter before moving on to the next stages. For the low-frequency path, however, we need to bring the 3.9107 GHz down to 310.7 MHz. To do this, another mixer is used, driven by a 600 MHz oscillator multiplied by 6, giving 3.6 GHz filtered by a bandpass filter to ensure a very pure LO signal. The math is simple. 3.9107 GHz minus 3.6 GHz equals to the expected 310.7 MHz. A high-pass filter removes the low-frequency mixing product, and then a PID diode, as we saw earlier, acts as an RF switch, allowing the analyzer to select between the high-frequency band 2.7 to 22 GHz or the low-frequency band 1 kHz to 2.9 GHz. In any case, once it leaves the second converter, we've reached the end of the RF section of this analyzer. From here on, everything depends on the electronic board, starting with board A15. This board takes over to bring the signal down to an even lower IF, and it also applies gain correction to compensate for non-linearities in the chain. The goal is to ensure amplitude linearity while preserving the dynamic range and noise floor I want to achieve by the end of this project. Back on the other side, the last step is to connect the CRT to board A2. On the 8560A, it uses a 10-pin dual-row header without a key, whereas this one has a keyed connector. I'm using a thin conductive tool to probe each pin of the 10-pin dual-row header. With a multimeter, I check where each wire goes, one by one. I do the same with the 8563A. This way I can confirm the correct orientation of the connector and be confident I won't fry the analyzer on the first power-up. Now I'm sure that the wiring is identical. So the last step is to remove the keying tab on the 10-pin dual-row header connector so it can fit into the male connector on the CRT board A17. You can't see much here, sorry, I'm right in front of it, but the board is connected. Done. I'll put it back in place. Now it's time to cross our fingers and close everything up. The long-awaited moment has arrived. To avoid spoiling the surprise, I check the unit is off before plugging it in. Okay, let's do it now. Good sign. The fan spins and the LEDs on the controller board all light up. The screen, however, stays dark. I'd rather turn it off and investigate further. Off camera, I tried adjusting the CRT brightness threshold, just in case it had drifted. So let's try again. You can see me hesitating to tweak it again, but in the end I decided the problem isn't there, and I should stop wasting my time on this dead end. At that point, I thought the issue might be related to the missing chip on the A2 controller board. According to the schematic, the missing component U202 is driving the 10V reference, and it's also right in the middle of generating the X and Y signals for the display. So that could explain indeed why I don't have any display on the screen. And here it is. I just received the replacement part, the MC34084P, which I will quickly solder onto the board. Nothing too exciting here. I've positioned the chip and I'm soldering the pins one by one. Pretty standard stuff. Without further suspense, let's try powering it up again. Yes! Great! Yes, I'm really happy to see it booting. You can see the CRT sweep. That's probably my fault from messing with the brightness threshold earlier. Several errors are showing up, including a recurring system error 201. I'm also taking this moment to observe what's displayed on the screen. It doesn't look very different from the 8560A, but one thing stands out. The default center frequency is 12.38 GHz, which is actually a good sign. The analyzer has moved onto the next stage of its startup sequence. Now it's trying to adjust the local oscillator, but apparently without success, since more errors are popping up again. And there we go. It looks like the startup procedure has finished. I'm testing a few buttons, but nothing seems to respond. I try some other commands. No, but still no reaction. No, that's not a good sign. No, definitely the analyzer isn't responding. I imagine one of the errors in the list might be related to this issue. In the meantime, I readjusted the CRT brightness threshold again, which removes the sweeps line. Now, I'd also like to adjust the focus since the image is still a bit blurry. You can see on the camera that I'm tweaking the sharpness with this control. The service manual explains that several potentiometers affect the focus, but I'm only adjusting this one since it's by far the most effective. There, it looks like much sharper now. The analyzer still isn't responding to any commands, but I think it's time to wrap up this video. It's already getting a bit long. That said, I've reached my main goals, namely rebuilding this unit and getting it to boot up again, even if there is still a lot of work ahead. For the next videos, I'll focus on one issue at a time so I can keep the format shorter and publish more regularly. If you haven't already, feel free to subscribe and hit the bell so you don't miss what's coming next. Thanks for sticking around until the end and see you very soon.